Good afternoon, everyone. Welcome to the Duke's Finding I&I webinar. We appreciate you taking the time out of your busy schedule to join us today. I head up marketing at Duke's, and today I'm honored to introduce our speaker, Mike Ping. Mike is the National Technical Manager at Duke's and has over 23 years of extensive experience in the wastewater industry. Mike's a licensed professional engineer in North and South Carolina and graduated from Clemson University with a degree in electrical engineering. Mike is going to explore the crucial techniques of level-only micro detection and provide an overview of level-only monitoring and how this data integrates with both traditional flow monitoring and pump station information. We encourage you to use the Zoom Q&A feature throughout the session, and we will address those questions at the end. And also, if we have enough time, we'll also open it up if you have any questions, even at the end. The only thing Mike asked me to say is he's not going to address any questions relative to the status of Clemson University's football team. That's off limits today. So thank you again for joining us today, and please join me in welcoming Mike Ping.
Brutal introduction there, but thank you. Yeah, so I'm Mike Ping, and we're going to run through micro detection for finding I&I. And I think this slide deck will be pretty close to about 30 minutes. So we'll just jump right in it. Yeah, so just to make sure we don't leave anybody behind, an overview of the basics of a wastewater system. There's some sort of producer of wastewater over on the left. That's an old Roman bathhouse or bathroom of some sort. Today in modern times that'd be a house, an industry, a business, but it would be piped up to the collection system photo to, the center photo there. Again, this one is very old, but the principle is it's the exact same principle. It's a conveyance system for the water, and it's a downward sloping channel of some sort. And it would make its way over to the top right, which in modern times today, it would be a biological treatment facility of some kind. And then from there, it would discharge into a receiving body of water. In today's world, that the conveyance system would likely, if it's installed today, be PVC pipes. You can see the kind of the greenish colored pipe there going into a manhole and onward to the wastewater treatment system. The important part of this is we're going to talk about I&I and micro detection and so forth is, these piping systems have a certain flow capacity, and that capacity cannot be changed unless somebody digs the pipe up, puts in a bigger pipe, or somehow can change the slope of the pipe, which it typically is not going to be happening. So diving into inflow and infiltration, or what's known as I&I, that we have a photo here, top left, that's a curb inlet that's engineered and built specifically to drain rainwater, right? And that ultimately should be piped up and discharge into some sort of receiving body through a channel of ditches or whatever the case may be. It could be little streams, creeks. It makes its way on out, right? So what it should not be doing is being conveyed to the sanitary sewer system, right? So with that, we'll kind of, I think a lot of people kind of get that, but maybe some of you have not have never dived into the numbers here. But just as an example here, a 2-acre area, let's say we get a rain event in this little town here, and our curb inlet up there in the top left has a 2-acre surface area of land, eventually funneling and draining its way into this stormwater inlet structure. And let's say we get a 1-inch rain event, right? Well, 1 inches, all this math works out to, you get this 1-inch kind of skating rink that's 2 acres big. It's over 50,000 gallons of volume, right? So thinking through that, if that 1-inch rain event happens over a 3-hour period, right? Rain events are not evenly distributed over a year, right? They come in different intensities, but in short duration. So if this 1-inch rain event is 3 hours, the resulting volumes here is you'd have, roughly 17,000 gallons per hour entering the sanitary sewer system. Do Paring that down to gallons per minute, 278 gallons per minute, and that value is representative of about 2,000 homes being connected to the sanitary system, for that 3-hour period. That's zero point 0.4 NGD, right? So that's one single defect, right? So I, can have a big impact. And in the red at the bottom, just kind of for entertainment purposes, the way this math works out, if there's a lot of 8-inch pipe out in the collection systems across the US. And if you have an 8-inch pipe and it's completely full of water and it's flowing at 1 foot per second, it's 156 gallons per minute. So very easily, right? That 278, it's a lot bigger value than 156. So it's just kind of, look, this is just a hypothetical, but just to try to make the point, the wastewater collection system can be easily overwhelmed. Okay, so now that we've kind of touched on I, what are some of the industry established methods in order to locate the I? And one, well-established tool methodology is area velocity flow monitoring. So, this is a set of equipment here. Happens to be the brand Hawk, which is now owned by Micrometer. And the white sensor on the left is called a FLODAR. The one in the red circle is a submerged area velocity sensor. And then there's an in-pipe ultrasonic in black, and then way over to the right is a standard ultrasonic that could be used over a flume or something like that. And just to give you a sense of size there, that cylinder of the logger, the dark logger with all the cords on it, um, it has in the base there 4 of the old lantern style batteries. So it's, I'm gonna say 8 or 9, 10 inches diameter, just kind of the size. So so this sensors, get placed into the wastewater collection system and it measures flow, right? So it's a great solution. And somebody that would, that hasn't been around this maybe would think straight out of the gate, well, great. Maybe if we have a 5 million foot system, let's put 5,000 of these out there. The limiting factor would be financial. This data is very expensive, as we'll soon see here in a minute. And so that'd be a great idea, except the utility would probably be out of money in about a week. But that's kind of in a nutshell the overview of area velocity. The way that the math works here, just another depiction here. You can see the sensor. I kind of drew a cord over to the pipe, but the basic formula, the mathematics behind measuring flow is the depth gets measured and it gets translated into a cross-sectional area. You can see this little A over here, and then it's also measuring the velocity, and that's the equation to calculate a flow rate, such as in gallons per minute. This is what it would look like out on the scene. You can see it's a very busy scene. So you have a field tech here. He's on a laptop, right? He's got the logger. You can see that cords. There's a guy down in the manhole. There's safety equipment, tripod, generator, road cone. This could be in the road, right? There are antennas to mount. There could be coring up the asphalt to place an antenna in, and so forth. It's a very busy scene, right? And what that translates into is, it's not inexpensive data, right? It's great to have gravity system flow data, but it's not inexpensive. Another common tool in the toolbox would be utility that utilizes their pump station data in order to try to figure out, which area contributing to each pump station is contributing what percent of I and the volumes and so forth. Very common to hear of people using run times. In a nutshell, that methodology involves a measurement of how long the pumps are running total, and just a basic comparison of, hey, these pumps normally run a grand total of 5 hours per day. They're turning on, turning off, turning on, and so forth as the wet well goes up and down, right? But let's say hypothetically that the pumps run a total of 5 hours. Here comes our 1-inch rain event, and all of a sudden it's running 12 hours for that day. So, you know, the utility would know, hey, there's a pretty severe reaction to the system in terms of inflow and infiltration. And then the pump station data could also be a measurement of the wet well level, lots of other sensors getting into kind of some full system SCADA and so forth, direct flow measurement. But this is a valuable tool in the toolbox, so to speak. So we, just to mention it, like, we'll talk about the toolbox here at Duke's. We offer a pump station monitoring service that includes all of these things. It's a subject all on its own. But it has kind of the iPhone generation, as I like to say, and it's allows a small utility to kind of go from A to Z in one quick step, and it's all in and includes all these parameters. So touching on level only monitoring, the subject, we talk what we call micro detection. That's the Duke's level only monitoring offering here. And here's a couple of photos going left or right. If you happen to know Stuart Tillery, that's him installing the level only, the micrometer. There's a spreader bar. There's lots of different like hardware contraptions and so forth. The purpose being to get the sensor, the middle photo there, get the sensor in the center placed above the channel in the center, and it's generally placed at the 6 o'clock or the effluent part of the manhole, and it's installed and it just sits there, and it measures the level of the water every 15 minutes. It logs it locally on the device. You can, on the far right, you can see kind of what these devices look like. So it's a very, very simple approach. And as we'll see, all of the work really is in the analysis piece of it. It's important to understand that, where this fits in the toolbox, as I like to say. So definitely, no, there are no utilities that are the same, right? So different projects line up and require different technologies and so forth. So, what we call micro detection, the level only, is certainly one of them. And then number two, area velocity or open channel flow monitoring, sometimes even called traditional flow monitoring. That's the DC powered device out in the manhole. Their alerting system, we have one here, the kind of the middle right photo, sewer alert. You can see the red stick there. That's just a basic alerting system that's intended to be in place for like long-term alerting and so forth, but it's part of it. And then we touched on the lift station monitoring. And then, a key piece for us is a very unique ability to mix and match these things as needed, right? Um, Rarely is one tool gonna, solve every problem. So we do a lot of combining of the micro detection level only with lift station or pump station data. We kind of use those some back and forth evenly, and we do a lot of micro detection and air velocity flow monitoring. And I've got a couple of examples of what those look like, and we'll touch on that towards the end here. And number six, I put my Duke's hat on here. I like to think we've got a very good, strong support team, and it takes a real solid team effort to pull these off, especially when it's combined service. We've got a staff of licensed engineers working kind of in the office, and then very fortunate to have a very good, some experienced, field crew guys that can handle these kind of more complicated installations out in the roadways and off-road and that sort of thing. So diving a little bit deeper into micro detection, number one, at its core, it's answering this fundamental, it's kind of making the statement of, hey, the INI, it's over here and not over there. It's not a flow study, right? We provide volumetric estimates, but that's it. It's over here, not over there. You can see this map. You'll see some color coding as we wheel through this slide deck. Typically, it's kind of industry standard. Red is going to would be equal to severe. Orange is kind of a moderate state. Yellow would be below that, fair, and green would be good. But this is a clip from a project that we did in the past. Each square, regardless of the color, is where a micrometer was placed. So quite often we place these as close together as every almost like 1,200 feet. And we sometimes use this characterize that as kind of street level INI. It's this methodology is very good for especially for the upper ranges of the system. If we go over, to this right, kind of top right part of the map, very low flow levels, and, other the area velocity, which, we do that too. That equipment really struggles in those applications. So it's great for that type of setup. So number four, the results include the heat map. This is an example of a heat map and estimated volumetric information there, gallons per minute and so forth. And again, the data is logged locally in the device. There's no telemetry. And then we take all of that out and then run it through the analysis tool. But in a nutshell, it's very cost effective. It's quick, as you'll see here, and it does a really good job to isolate the I&I areas. And we'll dig in deeper on that. So just kind of a overview of the project life cycle. Typically, field installation is happening within a couple of weeks of getting a notice to proceed or a green light in one way or the other. The equipment is installed. Generally speaking, certainly the eastern half of the United States, these projects last about 60 days. We set them up for 60 days, 2 months. And then out in more arid areas, especially kind of the Southwest, we have a contingency built on, and sometimes they last 90 days. We've had a few that needed to go on longer than that, but it's actually very rare. So, I would say 90% of these things are 60 days. So at the 80-day mark, we're removing the hardware out of the ground. All that stuff gets shipped back to our home office, and everything gets downloaded, brought into a calculator engine that cranks things out. Our engineering team performs that task, and generally we're providing results at about the 100-day mark. So it's a quick turnaround. So digging into the results and the data, just looking at some snapshots here, this is very typical of what things can look like. So I'll start with the one over on the right. This graph, you can see the kind of the red fuzzy line. You can see the axis on the left. That's a level in inches. So it's 0, 1, 2, 3 going up. Therefore, the level's kind of hovering around this half-inch mark. And the blue line is representative of the rain data. It's in increments of midnight to midnight, so it's a 24-hour increment. So on this particular, for this study, there's some pretty solid rain events. The two of them were over 2 inches, and the highest one there close to 3 inches. The point is, very little reaction to the rain event, right? Very little reaction. In contrast, the one on the left over there, this is the same study, kind of across town from one another, really in the same neighborhood, but not too far away geographically in distance, but same rain event. And you can see the red line, which is literally just the level in inches. It's jumping up to about 2.5 inches. And then we have our calculated estimated gallon per minute, right? The flow rate, and you can see what that is. So with that, we obviously do the math to say, hey, during this rain event, like the big one that's at close to 3 inches, we go through the math to estimate, hey, this rain event produced X total gallons in units of volume. So tying that in with a map and kind of the purpose of this study, again, you can see the heat map here, and the red and the green arrow. This red area, this is an ideal set of circumstances where, realistically, only 2 areas kind of quote lit up, right? The red one much more so than anywhere else. But this is an example of kind of typical results that we see. And the value proposition is to allow the utility to hit an area, get down to street level, and have a good understanding of, hey, the I&I is over here, it's not over there. That same basic statement. Our deliverables are produced in this dynamic platform. It's called Insight 360. And it's I'm too scared to operate this thing live here in in a team or Zoom's environment. But basically, there's a dynamic map over here where the user can click. You could click on the red area. That's the same one that we've been looking at here. And click on a green area and very quickly kind of just click around and get a real good feel very quickly. Hey, you kind of get a feel for what's going on, right? I remember in this particular study over here on the right, where it says food line, you have very like nothing going on from an I&I perspective. We rank everything, the kind of the distribution, and then present it in this, simple pie wheel. So very easy to understand. And, it's not the kind of type of study where we produce, 4 inches of paper and send it over, and it takes an engineer a month to read it and get their arms around it. These projects, typically, we send them over, we'll do a follow-up meeting, and it's the type of thing where the the utility and the group within the utility can look at it for 30 minutes. They've got their arms around it. It's pretty easy to understand. We'll do a follow-up meeting where they can ask questions about different things. And so it's just a practical tool to locate I&I. A close-up view here of the kind of what I'm going to call the meat and the potatoes. Just going left or right, this SANS, that's the asset identifier here. I truncated it, so it's kind of cut off there. But we have the priority, the pipe diameter, the maximum depth, minimum depth, the average dry level depth. And then we take that and put that in a percentage just to kind of see. Sometimes we see these that, the pipe is 80% full during dry weather, right? So it's worth calling out. So there's a additional value provided just having that many data points throughout, a study area. We run the time and surcharge, right? That's just the amount of time that the level is greater than the pipe diameter. Then we get into these estimated calculations where we're estimating the ADWF, or average dry weather flow rate, again in units of gallons per minute. The GWI, this column here, is groundwater infiltration. That's simply an indicator of groundwater infiltration. It's the flow values midnight to 5 a.m. that are called out. And then we have the total 4-day. That's the total volume over 4 days, additional volume during the rain event, right? So it has the dry weather volumes daily and so forth. Then this is the additional volume over the 4-day period during the wet weather period. So from there, we start to work the math, and as you work downstream, it could be that the I&I is attributed to a specific area, or it could be attributed to an area coming in from further upstream. So in this case here, this 540,000 gallons, that's the total that it saw. And of that total, 150,000 gallons is attributed to that specific area. From there, we provide the peaking factor calculation, which is the maximum instantaneous, like single measurement estimated flow rate divided by the average dry weather flow rate. And then we put this, you've got to have some way to calculate this so we can stack these guys up from worst to best or whatever. And our final rating, we put it in gallons per day. So it's this, where this orange arrow is, it's the total local divided by how much pipe is in that specific area. So we do that in inch miles, inches of diameter times length of pipe. And look, these areas aren't all the same amount of pipe, so we try to even it up with those with the denominator there, inch miles. And this is an oversimplified version of it, but let's say we had, the flow is going from left to right. I should have put an arrow in, but going left to right, it will just add up the I&I to see how this could work, right? So if there's an additional 50,000 gallons here, this one, maybe it's enough to turn it red. We get down to the next one. Well, it still only showed an additional 50. So there was no volume added in this middle section here where the green ones are. And then maybe it went up a little bit more, enough to quote, turn it red. And then working downstream, the grand total goes up to 90, let's say. So there was 10,000 gallons added in this wouldn't be a single segment. It'd probably be 5, 6 segments or something like that. But an additional amount was added to take it up to 90 and then so forth. So just kind of a simplified way to kind of understand how the math works. Again, a very simple and practical presentation. So not only the water sewer people, that would have a very good understanding of how this works, but these guys can hand it off to maybe a utility director that came up through the finance group or something like that. Who knows? But a lot of small towns, they have to hand these results over to a mayor or city council kind of person. Those people, we try to keep things to the point and in a way that it can be understood very quickly. And there's lots of data provided on the tail end of this in our online platform, but this stuff is very easy to digest. Yeah, and I just want to point out, experience wise, it's, this is not something that's new and we started doing this 3 months ago or anything like that. I mean, at Duke's, we've completed literally many hundreds of projects and with certainly many thousands of sites. So a good workflow that's well established and something that we've got a very high degree of confidence in. So that's kind of a snapshot of just micro detection. And I'm going to do a few slides here to just highlight, what it can look like when things are combined. And there's infinite possible combinations here. So just a couple to kind of highlight how this could work. So this one would be micro detection with some lift station data where we have, the aggregate run time over here on this table to the left. We've got an influent amount in gallons here, the minimum, maximum, instantaneous flow rates. We have rain and so forth. But we've done a number of these with combined lift station and micro detection, just where the application called for it, where generally where there's a collection system with a lift station and there's no data whatsoever coming out of the lift station. There's just no SCADA or anything. So it's a good way to kind of kill multiple birds with one stone. This is from a recent project, a different one. And, there were several things going on. It all flows from the left to the top right. And at the top right, I think just off the map, there's a pump station there where all of this goes to. Very important to note here, there are 2 towns that have no wastewater treatment dumping all of their city wastewater in through these pipes, right? So it's traversing through the utility that owns the treatment plant. So there's flow meters down here at the left. They wanted this particular utility, they needed exact numbers from each town, right? This system's getting completely overwhelmed. So there's a combination in this one of the micro detection up in the top right, kind of where the colors are, where the small boxes are, and then the stars are representative of a full area velocity flow meter. So this one had some really interesting results, and we captured the flow data, and then where the micrometers are, it's lesser cost, but so it allows for just more data ultimately for a fixed budget. So this is one that we're working on right now. This is a 1,000,000-foot system, right? Every blue box is a micrometer. So there's 170 of them in here. These projects range anywhere from 10 micrometers to 400 or 500, I think. So a big span there. But this one, we set this up, specific for this utility. There are 30 flow meters. You can see the yellow stars are a little bit hard to see. But the point is each micro area, if you divide 200 or divide 1,000,000 by 200, it comes out to 5,000 linear feet. So it does a nice job of really isolating the inflow and infiltration detection down to a very small area. So I kind of blew up one box just hypothetically. This project is in progress here, and yeah, I'm trying to get my cursor over there, but let's just say, like, hypothetically speaking, that these are the results. We don't have them for this project yet, but to get the point across, rarely is the inflow and infiltration evenly distributed over the system. more times than not concentrated to small areas or even a single instance, right? A single source location, right? So, you know, with this one, just hypothetically, we could say, 25% is coming from this area, 20% there. The green area, the green circles would be representative of, hey, there's minimal to no inflow and infiltration. That then there's the idea of like, okay, we found out what's going on. What could be next? Just to go 360 on this project area. It's one thing to locate I&I. The next step is you have to, something has to be done about it to fix the problem areas. This could be a potential fix, and it often is for us, right? So, you know, potentially that if the utility was considering TVing everything, let's say, right, that TV demand could go from the whole area, 1 million feet, down to, you know 15,000 or whatever the number is, just to get the point across here, a much reduced number, right? So quite often we're doing projects where we just go ahead and combine a line item and say, hey, we're gonna have a contingency here to TV up to 10% or something like that. Same with smoke testing, right? Smoke testing, a great tool to pinpoint inflow, especially, and a much more focused effort here, and kind of honing in the limited resources ultimately. And then, kind of taking the next step, what's next, right? Limited ongoing monitoring. There's no sanitary sewer system that's static, that's always changing. It's very dynamic, right? There's debris, there's pipes, the state of everything is ever changing, right? So, some things that we sometimes are doing, we've got the sewer alert, or overflow alert, as we call it now, the area velocity monitoring in the middle, and then pump station monitoring. Sometimes these things, ideally need to be in place to keep tabs on it over the long haul, but typically in a more limited and reduced capacity as compared with a study. So, we're at the end. So thank you for everybody for hanging in there. That was a quick 30 minutes on my side. And Mark, I'll turn it over to you.
Great, thanks, Mike. Yeah, we've got some questions, Mike, that have come in.
Okay.
A very respectful group, nothing about Clemson, so you're off the. One
Thank you for that.
uh, well, what are examples of where and which type of manhole or pipe this won't work in?
So for micro detection specifically, yeah, we're always on the lookout. One of the limitations definitely is areas that are just completely backed up. Or it could be that it's not backed up, but the utility tells us kind of in our, you know, period before the project kind of shaping things up, we're always asking, what happens when you guys get a healthy rain event? And if the answer is like, hey, this system is completely backed up and overflowing, then we know already what the answer is going to be. Our answer is going to be like, hey, your system gets backed up and overflows, right? So, you know, when we do that, that's typically where we're editing kind of the project and looking at another tool in the toolbox, like a flow meter, where maybe we can get that guy in during normal conditions. And if it fills up and the system gets overwhelmed, we still have the flow values, right? And we would put the micrometers further upstream. But generally speaking, as far as like the manhole specific structure itself, it's pretty much any manhole that we have access to.
Okay. Mike, here's the next one, and it's a little bit close to the answer to this one, but I just want to make sure we address it, which is, how do you decide when to use the flow monitoring equipment, and or when do you use the micro detection units?
Yeah, good question. So again, it's kind of what the previous answer is is lined up with that question. But the example that I utilized towards the end is, a utility that's accepting flow from other utilities. It could be that they're accepting flow from a very large industry, right? And it could be that they just want to know exactly how many gallons is entering a lift station, right? they want to answer ultimately the what we characterize micro detection is like, hey, we're going to learn the ionize over here, not over there. Somebody's looking for an answer that's deeper than that, that says, hey, I want to know that, plus I want to know exactly how many gallons it is. Right. So it's a combination of a couple of things. Hopefully that spells it out a little bit.
Okay. Mike, another question that was asked is, do you sell the devices? Do you rent or do you rent them?
Yeah, that's a great question, and I'm glad that I didn't probably cover that specifically. This is a turnkey service. We do not sell hardware. Anything that I talked about here, there is no hardware selling. We provide this as a service, and that's it. And adding on to that, I would say realistically, any of these services, especially flow monitoring and the micro detection, I mean, the amount of effort that it takes to get, we can do it because we're kind of like the race team pit crew, right? We've got guys that do that every day. They can change a wheel in 10 seconds, where if I pull out my car and a jack out here and do it all on my own, it takes me 30 minutes just to round up the tools, right? So it would be it's not that it's impossible, but it would be very hard. I'll leave it at that.
Yeah. Another question, Mike, is there any type of order of magnitude cost for the micro detection installation work and results reporting?
It's an all-in number. We typically price it up per linear foot. Okay, so but not all the time. I would say it's 60/40. Sometimes it's project specific, and sometimes it's per linear foot. And I have to say that because like we do work on, the, let's say like Los Angeles or big city Northeast kind of places where, there's prevailing wages and the cost structure is very different than, I live in kind of rural South Carolina. It's very different. So I'll say this: we do a lot of projects that are $50,000 to 300 kind of thing. There's just that's kind of the bell curve, and there's projects that are 20,000 feet to hundreds of thousands of 500,000 or 800,000 linear feet. So the answer is not clear because we've got the ability to space these guys apart, right? So if a utility says, look, we've like the one that I showed there, they were, look, we've got this amount of money, right? So any of these projects, they're great, but they've got to get married up to an available fund, right? So as a technical guy, I want to pack as much in there as possible to produce the best result, right? So we have the ability to space this stuff apart, and we'll stretch it out if we come back with an initial offering of, let's say, $100,000, and hey, we only have 80. We've got the ability to kind of space everything apart a little bit more if we wanted to, and kind of reduce it. So that's a long-winded answer, but hopefully that spells it out.
Yeah, and Mike, there's a question I think that is close to what you just answered, but I just want to make sure, and that was, is there a minimum amount of meters that are really needed?
Yeah, it's a good question. So from a technical standpoint, what we can't do is take 1 meter and put it in, right? Like we need kind of, the more we have, the more the spider web of meters get built out, the better, the stronger the results are, the higher quality it is, because, you know, the, our estimator and calculations, it's on its own. Uh, it's just a lot stronger when we have 10 or 100, right? That estimation just, it gets tightened up, the mathematics do, as we get bigger and bigger. So hopefully that makes sense, but there's no, there's no real minimum. We could put one in, I guess, if we wanted to. You'd get the level, and then the estimated values would be dependent. I would say that.
Okay. And then Mike, I'm gonna give you another one about what would a $50,000 cost represent in system size or linear feet? I know that's a tough. tough
No,
one.
it's okay. It's valid because again, because of the ability to stretch things, sometimes we'll do more of a standard project and that 50,000 could be over a 30 or 40,000 foot basin total. But sometimes we stretch these things out and it could be 100,000 foot, but typically it would be probably 40, 50 kind of thing. And don't, please, whoever, if you're still listening, don't hold me to that, but just to give you a general feel, that's kind of what it would be.
Okay. Most of our 16,000 plus manholes are eccentric cone. So most flow channels aren't centered below the casting. How do you offset the level sensor, especially in extreme situations?
Yeah, so good question, but it gets encountered all the time. So we've got a spreader bar and we've got a bunch of, I call it the erector kit, the metal toys that you play with when you're a kid with all the bolting and building stuff or Legos or whatever. But we've got lots of hardware and tools to get that over to where if the sensor could be 3 or 4 feet over from the center of the manhole. So um, it's a bunch of piping and stuff that's just been developed over the years. I mean, we're in a position now to where you get to. I think anything you do, you get to project 3 and 400, you're a lot better than at project 3 and 4. So all that sort of stuff been worked out long ago.
Um, are meters monitored during the study for data collection or only checked upon removal?
Only checked upon for the micrometers, only checked upon removal. Great question. And the answer is this, the data capture is not 100%, right? But almost in every case, it doesn't need to be, right? We'll have meters that show up that say, hey, there's little reaction anywhere above this. So if there's meters wherever above that, it almost doesn't matter, right? We know that at this point there's no reaction, and there's ways around that. So and when we do this high density approach where they're every 6 or 7 manholes, losing one, we actually put in a few extra counting on it, right? So it's all that all shakes out in the end, and I think my feeling is it doesn't impact the results.
Mike, you reference various tools on what should be used for locating INI, and then you also reference different tools like for ongoing monitoring. Can you just quickly sort of differentiate between the two?
Yeah, so I think the answer would be a function of like the specific what the goal is, right? So this micro detection method is built around, hey, we need to find the INI, but we only have this much money available, right? There's only this much funding. So our goal is to pack as much data in as we can to locate and get that area as small as we can. And I went up like this slide kind of explains it where this guy here where just as an example to kind of answer the question, if we were over here and we determine like, hey, this area over here lights up, then when you look in the red box, really it's just this small area here. You're down in that 5,000 foot range. So there's always going to be a follow-up action, right? There's going to be TV, there's going to be other things happening in order to, hey, we found the INI area. Now what? We need to fix it, right? So you have to find where that fix needs to happen and what that fix is. And those steps and that potential rehab are much bigger dollars, right? So there's a big value in paring all that potential expensive inspection down to as little as possible. And look, we like to do TV, we do that too, right? So, call us and say TV the million feet and that's what you want to do, then so be it, right? But this method is to kind of reduce that down is the principle of it.
Hey, Mike, one question that came in, on your last slide, what's missing is your email address. So do you want to provide to the team your email address if they have any questions and want to contact you directly?
I will. I'll put it right here.
There we go. Thanks.
mping@dukes.com.
Okay, I had another one come in. How do you correlate INI to rainfall? Do you normalize it to a typical event or just quantify it to the total?
We do correlate it to a specific event, 100%. So our methodology is we take a time period of data around the signature rain event, and we take a time period of the data that best fits dry weather, and we're comparing and contrasting and doing some math between those two, right? But we don't take it as far as like hydraulic model level data to where we're saying, hey, the intensity is X per every 15 minutes. Our rainfall is measured in midnight to midnight increments. So we have 2.1 and we're just looking for the reaction. And the reasoning behind that is like we can do further, and we do studies like that, the more intensive ones. But this service is just to say, hey, we want to find where the INI is. Our ship is sinking. Where's the hole? Right? So we try to keep that at a minimum, and our workflow is very established and efficient to keep the cost down.
Right. I'm just making sure I got all of them.
Nothing about Clemson.
No, they're
I'm surprised.
very nice crowd, very respectful crowd. Um, well, with that, we maybe have a few minutes if somebody wants to. We will open it up. The group has really asked a lot of questions, but if somebody has come up with one that they want to, ask live. Somebody did say not Clemson, but let's talk about the Aggies. If somebody does have a question and they do want to, ask it live and want to, sort of raise your hand, and then we'll take you off mute. And we'll just give it a few minutes if somebody wants to go live. Otherwise, then we may wrap some things up. Oh, Mike, they're coming after you now.
Oh no.
How bad will Syracuse beat Clemson this coming weekend?
By a little bit, not by too much.
Mm,
So
okay,
I don't know if y'all can hear me or not.
we can hear you now.
And
Yes,
Yes,
we.
this is David over at Anniston, and I just wanted to take a minute to say that we have done several of these studies, and we have found some incredibly good information from it. These heat maps that they give you show you exactly where you need to go out and look. And we're signing up to do another one. We're doing part of our system every year, whatever we can afford to budget. So, I don't really have a question as much as I have a 100%. This is something I think every system should be interested in. So,
appreciate that. That's kind of you. Thank you for that.
Thanks, David.
I just worked on your project this morning.
yeah, Stuart said he was sending something over. I think there was a little miscommunication on the footage,
Yeah.
but I think we'll get that worked out.
Yeah. Yeah. We'll get you squared away. Any other ones?
Back off.
No more right now, Mike. So I think you got a compliment. Great presentation. See you at WEFTech. So with that, hey, Lewis, with that, I want to thank Mike for putting this material together. I know finding I&I is a challenge for all of us, and we appreciate you spending the time with us this afternoon. The questions were great, and looking forward to helping you find the elusive I&I and different ways we can do it in a quick, cost-effective manner to help isolate, locate, and resolve these issues. So thanks everyone for joining us today, and we wish you a good, safe, happy day. Thanks everyone.
Appreciate it.